Yeah, good evening. Welcome now to today's session where we shall be discussing on a subtopic in work, energy, power and machines, and that is the part of machines. You are all welcomed. Invite a friend. Don't forget to subscribe towards the channel, and may God bless you. Enjoy your lesson. So now we are having the introduction part of this chapter, and we have some terms that we need to define, and therefore we shall kick all the way from the term machine itself. So, what is a machine? So, welcome. So, what is a machine? And this is a device that enables work to be done easier or easily or with convenience. Convenience. So that is the term machine. So in case you are asked what is a machine, you can be asked. So you need to define it in that manner. So do not ignore these uh, little words because we keep on advancing in the mode of testing. Then we have to talk what is happening within a machine, where we have to apply the force and how will happen to when you are doing the work. Remember, you're working or you are racing against a load. Therefore, in a machine, a force is applied at one point uh, and is used to generate a force at another point to overcome a load. So far so good. We have known that in a machine, we have the machine itself. We have some one side where we need to apply some force, and we have another part where we have to work against a load. Therefore, now we have some simple machines that we all know. So we have one, we have the levers, we have the police, we have the hydraulic press, and we have the gears. Therefore, we can look at the terms that are used in these parts, where we'll start The terms are 5 in number, and we have the first one, which is the effort. So what is the meaning of effort? Is the force applied soon I'll be better in my handwriting. Force applied to the machine. We all know that SI unit for this one is in Newton because we are talking of a force. Then we have number 2, where we have the load. It is the force exerted by the machine So if you are already there, maybe you can give a comment plus where you are coming from. I'll be able to see you, then I shout your name. Number 3, we have what we call mechanical advantage. And this one is the ratio of the load to the effort. Ratio of the load to the effort. Meaning that this one is denoted as MA. Therefore, you can say MA is given by the load over effort. And since this is a ratio, then it doesn't have the units. We can have the fourth term, where we have, but before we move to the fourth term, we can give out some example here. Where we are told if a force of if a force of 30 newtons is used to overcome a load of 120 newtons, then what is the mechanical advantage? So we say mechanical advantage will be given by the load over effort. Our load here is of 120 newtons. Then you divide by our effort, which is of 30. And in this case, we have 4S, our answer. Okay. So now we can still continue. There are some things that we need to note, where we will say that the mechanical advantage of a machine is dependent on friction between the moving parts of we are all talking the parts of a machine, sorry, and the weight of the parts of the machine. Therefore, how does it have to impact on this? The parts of the machine that have to be lifted, that have to be lifted when operating. The greater the greater the friction, the smaller the mechanical advantage. This is just the introduction part. So we have to deal with the terms and the definition before we get into the serious other corner of working. So now we have velocity ratio as the fourth one. This one is denoted as VR and is said to be the ratio of distance moved by effort dE to the distance moved by the load dL. So we can say velocity ratio is given by effort distance over load distance. Well, we can denote them as dE over dL, like that. We have another one, which is the efficiency. And that is noted by this sign. And then is the ratio of the work done on the load into brackets. This is work output to the work done by the effort, which is work inputs. Okay, so this one is where we are saying that the work done on the Lord, or yes, work done on the Lord will be given by the Lord times Lord distance. That is L times DL over, sorry, I'm moving so fast. Lord. Then we have work done on the work done by the effort. Will be the effort times the effort distance. That is E times DE. Now, let's use now the symbols where we'll say our efficiency will be given by the work done on the load over work done by effort. Sorry, I've not finished the part. So this is work output. This is work input times 100%. Now let's get into the normal formula. Let's get into the normal formula where we said the work output will be the load times the load distance, and the work input will be the effort times the effort distance. Therefore, we can say this is given by L times dL over E times dE, like that. Previously, we know that load over A will be given as mechanical advantage. And we know that dE over dL will be given as our velocity ratio. So what is in the picture? You pick these parts and these other parts. You'll find that this part is given as 1 over VR because it is dL over dE is given as 1 over VR. Therefore, we can say efficiency is also given by the mechanical advantage of velocity ratio times 100%. And we have an example here. Example. where we are told that in a machine, the load is moved 2 meters when the effort when the effort moves 8 meters. If an effort of 20 newtons is used to raise a load of 60 newtons, determine the efficiency of the machine. So now we need to solve where we'll say that efficiency by MA over VR times 100%. We know that our mechanical advantage is equals to load over effort, and in this case it is 60 over 20, where we get 3. Whereas our velocity ratio, we say it is effort distance dE over dL. And in this case, effort distance is 8, whereas our load moves 2. So it is 8 divided by 2, you get 4. So now we can substitute this one in our formula here. So we have the efficiency being given by 3 divided by 4 times 100%. And this will give us 75%. So the machine is 75% efficient. Is 75. So can see Uhuru Malikuni. Does the mechanical advantage have units? No. The reason is because we are doing some ratios. So the mechanical advantage, we said, it is load over effort. So load is in newtons. The effort is still in newtons. Therefore, we do expect it to have no units. You can also refer to wherever we are having ratios, we don't give units. So I have seen you, Uhuru Malikuni. Now let's continue. We have some other section where I had prepared And in this case is when it comes to these machines. And for today, we will touch on the wheel and axle, and then we look at the inclined plane so that you can have at least some touch of 1, 2, 3 in these simple machines. Then the other machines that we mentioned, we shall continue tomorrow. Therefore, I would like to take you somewhere where we are having uh, the wheel and the axle. So here we have the wheel and the axle. So it consists of a large wheel of radius R attached. So allow me to use this shading now. Of radius R, capital R, and hexo of radius a small r. Then the effort is applied on the wheel. You can see from the diagram. You can see clearly from the diagram that we are having there. Then on the wheel, while the load is attached to the axle. An example of the wheel and axle is a winch used to draw water from the well. So this one is happening more so in the coastal areas where we have some wells which are very short. So we have the winch. It is like this. So how will we get the issue to do with mechanical advantage and the velocity ratio efficiency? So in one complete revolution, the wheel moves through a distance of 2 pi r. In one complete oscillation, that is a revolution, while the load moves through 2 pi r. In short, this is the circumference of the wheel, whereas this one is the circumference of the small axle. You can just call it the small axle. So the velocity ratio of the wheel will be given by the circumference of the wheel over the circumference of the axle. And this one will be, you'll see that the 2 pi is common. Therefore, it cancels out. And we are left with r over small r. Therefore, you can say the velocity ratio is the radius of the wheel over the radius of the axle. We can make an example here where we are told that a wheel and axle is used to raise a load of 300 newtons by a force of 50 newtons to the rim of the wheel. So we are having a load of 300 newtons and we are having a force, so effort of 50 newtons applied to the rim of the wheel. If the radius of the wheel and the axle, so the radius we have the capital R is 85 and the other one is 10 respectively. Calculate the mechanical advantage and the efficiency. So mechanical advantage is very straightforward. It is the load over the effort. So load over effort, where we shall pick our load of 300 newtons over the effort of 50 newtons. And in this case, we shall arrive at 6. And we have said that mechanical advantage doesn't have the units. Then now we have the velocity ratio, where we say it is given by the radius of the wheel over the radius of the axle. And now we have to convert these units into SI units, where it becomes the radius of the large, that is the wheel, becomes 0.85, because 1 meter is equivalent to 100 centimeters. So what about 85 centimeters? So you get at 0.8. The other one becomes 0.1, 0, and this becomes 85. I'm sure somebody is asking himself or herself, why do we substitute 0.10 instead of 0.1? The moment you are converting units, you need to convert it and count the number of the digits in it. Do not exclude any, because it is easier to say 10 centimeters is equivalent to 0.1 meter. It is okay. But now when it comes to the substitution, substituting 0.1 is not accurate, because if you look at, if you meet your workmates, an examiner who looks at the real work, then the real work will go for 0.10 meters. Then now, this becomes mechanical advantage over VR times 100%, and this will give you 70.59%. That is an example of the wheel and the hexel. Then now, I want us to touch something briefly on the inclined plane. On the inclined plane. And then give out an example, and then we stop at that. So now, let's look at inclined plane. So now we may proceed. Let me give us a drawing here. we have this angle theta. We can call this one as our H. We can call this one to be our L. And then we can give a load that is moving along this inclined plane. Load in that manner. So now we want to extract how will we arrive at the velocity ratio of an inclined plane. So in this inclined plane, we are able John from Mavoko Boys, welcome and thank you for tuning into us. So this one is used to to help load vehicles or move heavy loads through increasing the distance of the load. So if you look at it very well, then we shall say that velocity ratio will be given by the effort distance, as we said, which is dE over the load distance, dL. Now the question is, where do we have the effort distance and where do you have the load distance? Remember, the person who is pushing, or else the applied force, will be here. So it is pushing this load along the L distance, where you can see our L here. Then the load, naturally, it was supposed to come from the ground and be lifted through H. So that one becomes our load distance. So this one, if I may show it this way, this one, it is that one, whereas this one is this one. So we can say this is L over H. But now there is something that we need to understand from this section, because this an inclined plane assumes the shape of a right angled triangle. Therefore, from the SOHCAHTOA, then sin theta will be given by the opposite over the hypotenuse, which is H over L. So now in this case, our H will be given by L sin theta. But look at the first equation. So this was our first equation. And now we call this one to be our second equation. Now, if we say we have to substitute our h here in the first equation. So substituting h in equation 1, then VR will be the same as our L over L sine theta. The L cancels out, so L cancels out, and we are left with VR is the same as 1 over sine theta. So instead of going or going through a very long process, then we can say our VR is given by 1 over sine theta. I'm having a question, but it is a bit long, but we be patient. I put it down, then we work on it very fast so that we can have a wonderful lesson of good business. Therefore, allow me write the question. Here. A man uses the inclined plane to lift a 50 kg load through a vertical height of 4 meters. The inclined plane makes an angle of 30 degrees with the horizontal surface. If the efficiency of the inclined plane is 72%, calculate 1. The effort moved, the effort needed to move the load up the inclined plane at a constant velocity. Then we have part 2, the work done against friction. in raising the load through the heights of 4 meters. So in this case, I'll draft the inclined plane for this question. Because we have heard the question very well. So we need to interpret it. We are told that the height that needs that the load must be raised through is 4 meters. It is inclined at an angle of 30 degrees. So now we are having 30 degrees here. Thank you, Abazenda. He is following from Kikuyu. In addition, is trying to be specific. Kikuyu is in Kenya. Thank you so much, brother, for tuning and to us. This is Sending Grace Studios. So now we are saying that this height here is of 4 meters. That is the main agenda of the inclined plane. We are not lifting up the load directly, but we are using this inclined plane here. So we are saying we are having a load of 50 kg. Then it must be moved through this distance. Now the first question was the effort needed to move the load up the inclined plane at a constant velocity. So before we get into the effort, then we must go through a certain process where we shall first look at what is the velocity ratio. So our velocity ratio here, we say we can go through a shortcut 1 over sine theta, which will be the same as 1 over sine 30. And in this case, we'll be arriving at 2. That will be arriving at 2. The board is becoming shaky, but don't worry. Everything will be all right. So now the next thing, we need to analyze the question. So we have been given a load. Sorry, we have been given, okay, we are having a load of 50 kg, and this translates to 500 newtons through mg. So we will be getting a load of 500 newtons. Then the other thing that we have been given, we have the sine theta, and we are having the distance that will be moved, and this will be the load distance. The load distance we have been given as 4 meters. Now let's get back to the formula where we can say efficiency is given by mechanical advantage over velocity ratio times 100%. In this case, we are given as a velocity ratio to be 72% is equivalent to, we do not have the mechanical advantage because we do not have the effort. So it will be MA over VR, which we got as 2 times 100%. So this becomes this becomes, if we make MA to be the subject of the formula, we will say it is 72 out of 100 72 out of 100 times 2, and this becomes 144 out of 100, giving us 1.44. So if the mechanical advantage is 1.44, then you can say mechanical advantage is given by the load over the effort. So from mechanical advantage is given by the load over the effort, then the load, we have it from the weight is equals to mg. We have the 50 kilograms times 10, where we'll be arriving at 500 newtons, this one. So we'll say that our 1.44 will be given by the 500 divided by E. Then we make E the subject of the formula. Our E becomes 500 divided by 1.44. And this is giving us 347.2 newtons. So let me confirm this one from my calculator. So it is 347.22. I have picked to 1 decimal point. So you can see my shading is blocking some parts. Maybe I repeat from where that part had been blocked. So if I do away with this section, then I will be able to help you retrieve what we had gone through. So this is what I had said previously. So our mechanical advantage is 1.44. Then mechanical advantage is given by the load over effort. Then our load in this case will be a mass of 50 kg, which is 50, then times 10, you arrive at 500 newtons, the one that I had previously noted here. So this now becomes 1.44 is equals to 500 divided by our E, the one that we are being asked. Therefore, making our E the subject of the formula, then it will be it will be 500 divided by 1.44. Then this takes us to 347.2 newtons. So this becomes our effort, and that is what we had been asked in the first question. So now we move on now to the next part, where we are asked the work done against friction in raising the load through the height of 4 meters. So in this case, the work done against friction will be given as the work input minus the work output. So we'll say that work done Work done against friction is given by the work input minus work output. So let's look at this diagram clearly. Allow me try to expand it. In this manner. This one will be enough for viewing. So now we are saying the work input minus the work output. So which one will be greater? If you look at this one, the work output is the work that is done on the load, whereas the work input is the work, sorry, I'm saying the work input will be the work done by the effort, whereas the work output will be the one done by the load moving or rising at this distance of 4 meters. Because naturally, we can just lift the body. We can just lift the body. If we assume the body was at this ground here, this is 50 kilograms. Then you can just lift it directly like that. So the main focus of this inclined plane is just to place the mass of 50 kg through a distance of 4 meters from the ground. But now we are using a longer method to make the work easier. Therefore, from what you have seen in that diagram, then now we shall come back to our working in this manner. So our work output will be the same as the work done racing through 4 meters. That is the work output. So what is the mass here? If I use a different shading, then we are talking of lifting this one like this. That will be the work output. The main agenda is just to ensure that this load comes up. So it will be the load itself times load distance. And this is a load of 50 kilograms. When you convert into load, it will be 500 newtons. Then times the load distance, which is 4 meters. Sorry, and this will lead us to 2,000 joules. This will be 2,000 joules, like that. Now the other one will be the work input. Work input. And this case, sorry, before we go further, then we can also say that this one can also be done by the gravitational potential energy, GPE, where we say mgh. So this one can also be said to be mass of 50 times 10 newtons per kg times our height of 4 meters. Then this one will take us back to the 2,000. So our work input will be the work done, that is the efforts applied times the effort distance. And what is it now? Our effort, we have seen that we got it as 347.2 newtons. So we say 347.2 newtons times a distance that we have not calculated it, but we shall be arriving at it. So it is this distance in that manner. So how will we arrive at that? So we can say from the SOHCAHTOA, then sine 30 from SOH, then our sine 30 will be the same as opposite of 4 divided by, let's award it to be like L times L. So over L. So our L will be the same as 4 sine 30. For sine 30. Let me work it out. So from the other calculator, I'm finding that sine 30 is 0.5. So this is 4 times 0.5. And this will lead us to 2. Therefore, and this is supposed to be 2 meters. Sorry, it cannot be 2. So allow me get back. Allow me get back somewhere I've gone wrong. Making L the subject, the formula is supposed to be 4 divided by sine 30. So it's supposed to be 4 divided by 0.5. And this one is becoming 8 meters. Now it is making some sense. So now this becomes 347.2 times 8. Let's get to it. Times 347.2, where we shall be arriving at 2776.6 joules. Now, the work done against friction will be the work input minus the work output. So the input will be 2776.6 minus 2000. Then this one will lead us to 776 0.6 newtons. Sorry, it is supposed to be joules. Sorry. We are talking of work done. So that gives us the work, the extra work that was meant. So so that the mass of 50 kilograms could move. Thank you so much for those who have tuned in. May God bless you. Let's see each other in the next part or in the next session where we shall be discussing the other machines. Have a blessed night. See you next time.